Before we start on the theory behind the ideal gas law experiment, just a quick warning that this experiment is quite difficult. It's designed to help you practice some of the hardest parts of the thermal concepts of the thermal topic. So it's really important that you come well prepared to the lab. Okay, so with that warning, on to the theory. So in this experiment, you're going to be using the ideal gas law. To start with, you're going to be placing masses on a syringe. So you'll have a syringe like this one. This is the syringe you'll be using, and you're going to be placing masses on top of it. Now, as you know from Physics 1A, when you place masses on something, there's a weight force. So by placing masses up here, you'll be exerting a weight force on this plunger here. And you're going to be using this to calculate, and then you're going to measure the pressure inside the syringe. So as hopefully you'll remember, the pressure is equal to force over area. And this area here is the cross-sectional area of the syringe. So the area of this surface here. So you'll actually be able to measure this in the lab, because for this syringe, you'll be able to measure the volumes, and you'll also use your ruler to measure the height. And the volume divided by the height is going to give you the cross-sectional area for that plunger. So pressure equals force over area. In this case, the force is applied by the weights. So when you add weight, you'll get a change in pressure, and that'll equal mg on A, where A is the cross-sectional area. Now, one important thing to remember is that we are in the lab, and because the lab is on Earth, we've got atmospheric pressure acting on us. So the total pressure experienced by the syringe is going to be the atmospheric pressure, which should be 1.01 times 10 to the 5 pascals, but you'll be able to measure it to check that, plus the additional pressure from the weight force. So in addition to this, you're going to be using the ideal gas law, which tells us that PV is equal to nRT. Now, in this first part of the experiment, you're going to fill the syringe up to some initial volume, and then you're not going to let the air in or out after you've done that. So because the air is not going in or out, N, the number of moles, will remain constant. R, the gas constant, is just a constant. And with the temperature, for this part, you're actually going to wait for the syringe to come to thermal equilibrium with the surroundings after you add each of the masses. So the temperature is actually going to be constant as well. It's just going to be the room temperature. So we've got every term here is constant. So this will allow us to use that PV is constant, and so the initial pressure times the initial volume is going to equal any final pressure times final volume. So you'll be making use of this equation in the first part of the experiment as well. So that's the theory that you're going to need for part 1. In part 2 of this experiment, you're going to be taking the gas inside the syringe through a cycle. So first you're going to be doing an adiabatic compression, then you'll have an isovolumetric process where it's going to be coming to thermal equilibrium with the room, and then you're going to do an isothermal expansion where it's slowly going to come back up to its initial volume. So in order to understand what's going on there, you're going to need to understand what each of the terms that we've just used means. So let's go through them. An adiabatic process is one in which no heat is transferred. So Q is equal to 0. Now, how you're going to achieve this in the lab is you're going to compress it very quickly. So if you do something quickly, then there's no time for the heat to be transferred, and so Q is equal to 0. Now, for an adiabatic process, the gas also obeys the equation PV to the gamma is equal to the constant. So you would have seen this in lectures, where gamma is equal to Cp on Cv, the specific heat at constant pressure over the specific heat at constant volume, and that is equal to F plus 2 on F, where F is the number of degrees of freedom. Now, inside this syringe, I've just got air because I've just filled it up from the lab, and air is mainly comprised of nitrogen, N2, and oxygen, O2. So air is basically a diatomic ideal gas. So as you hopefully know, a diatomic gas at room temperature has 5 degrees of freedom. It's got 3 translational degrees of freedom and 2 rotational degrees of freedom. So at room temperature, we've got F is equal to 5 at room temperature and pressure. So this tells us that gamma is equal to 7 on 5, or 1.4 for air at room temperature. So you'll be using this equation in the lab to describe that adiabatic process. Now, another process that you're going to be looking at in this cycle is an isothermal expansion. Now, all of part 1 was isothermal because we were giving it time to come to thermal equilibrium with the surroundings. So isothermal processes tend to be slow because this allows time for the heat to be transferred and for everything to reach the surrounding temperature. So the equations that we have that explain, well, or describe isothermal processes are, we've got that there's no change in temperature, and so we know that because the internal energy is given by F over 2 nR delta T, and the temperature is not changing, there is going to be no change in the internal energy. Now, the other thing that we know that we showed in part 1 was that PV is equal to constant, and that's because nR and T are all not changing, so this is constant. So the final process you're going to be doing in your cycle is an isovolumetric process, where you're just going to be letting it come to thermal equilibrium with the surroundings without changing the volume. So isovolumetric is one in which the change in volume is equal to 0. And as we're not changing the volume, we're not doing any work on the gas inside that syringe. And so for isovolumetric processes, the work is equal to 0. And looking at the ideal gas law, the V is constant, so V equals constant, which is equal to nRT over the pressure, just rearranging the ideal gas law. So nRT on pressure is constant. So when you've measured everything for your cycle, your volumes, your temperatures, and your pressures, you're going to be looking at how the first law of thermodynamics applies in this case. So you'll also need to know your first law. Which is just that the change in the internal energy is equal to the heat transferred into the system plus the work done on the system. So you'll be applying this to these different cases here. Here you know what that the Q is 0. In the isothermal process, we know that the change in internal energy is 0, and in the isovolumetric process, we know that the work is 0. So for this experiment, you're going to need a ruler for measuring the height of your syringe and a pencil for drawing the graph of the cycle. So please remember to bring a ruler and a pencil to the lab with you. During this experiment, you're going to be using this syringe here. You can read the volumes off the side of the syringe. At the bottom of the syringe, there's a temperature sensor. The temperature sensor is a thermocouple device, which does take a very small increment of time to come to thermal equilibrium with the surroundings. So just keep that in mind when you are measuring the temperature. It's not an instantaneous temperature. It does take a lot less than a second, but a very small increment of time to read off the temperature. So you're not actually going to be able to measure the absolute maximum temperature. Now, to connect the temperature sensor, you've got a cord at the bottom of the syringe, and you're just going to plug that into this passport device, and this will now be logging the temperature at the bottom of that syringe. Now, this syringe also has a pressure sensor, so that's connected to the passport device through this tube here. Now, this device has a screw and click mechanism. It's really important that you don't pull and yank this connector here, because that is going to break the syringe. So to connect this to the passport device, you just put it on and then screw it round, and you'll hear a little click, and it's then locked into place. So that's the pressure sensor there. When you're putting air into or out of the syringe, you need to have this pressure sensor disconnected so that the air can flow freely through this tube here. So once you've connected this to the passport device, you're then going to need to connect the passport device directly to the computer. So it's just got a USB cord that you will be plugging into the computer. So let's have a look now at what happens when we plug it into the computer so that we can get the software all set up and ready to record. For this experiment, you're going to be using the capstone software. You open it up from the dock down the bottom. The icon is like a little pyramid. So click on that to open it, and then you'll need to open the ideal gas law template by going Open Experiment and choosing the ideal gas law from within the Physics 1A experiment folder. When you've done that, you should see an absolute pressure versus time graph and temperature versus time graph on your screen. When you're ready to record data, you'll hit the little red record button down in the bottom left-hand corner. So let's see how to get ready to record that data now. So for part 1 of the experiment, you're going to need 60 milliliters of air inside the syringe. So make sure that the pressure sensor is disconnected, pull the plunger up till it measures 60 milliliters, and then connect the pressure sensor back to the syringe. Okay, now we're going to be placing masses on this syringe, so we need the syringe to be nice and stationary. So with the boss head and clamp the syringe with the base of the syringe flat on the cork mat. You don't need to clamp it too tightly. This is just to provide a bit of stability so that it doesn't wobble about as we're taking the measurements. Now, before we start, we're going to need to get some initial measurements so that we know what the atmospheric pressure, or at least the pressure inside that syringe, are. So you can now press the collect button on your computer, or the start button. And this will start collecting the data. So now what we're going to do is we're going to place the masses on top of the syringe to start applying that force and changing the pressure. So to start with, we're going to add 1.5 kilos to the syringe. So we're going to need the 500 gram mass holder with 2 of these 500 gram masses on it. Now, with this experiment, it's really important that everything is carefully aligned vertically. We don't want these masses applying any sidewards force onto the syringe. We want everything vertically up and down. And again with this clamp at the top, this is not actually to hold these masses, it's just to provide some stability and stop them falling off the clamp. So this is just resting on the top there so that the entire 1.5 kilograms is applying a weight force downwards. So just make sure that everything is nicely aligned vertically. Now it's going to take a very short time for this syringe to come to thermal equilibrium with the room temperature, and you'll be able to see when that has happened on your temperature graph, because you're going to get a little blip when you put the masses on, and then it's going to return nicely to the room temperature. So that'll be the measurement that you'll want to be taking for this part. You can measure the pressure and temperature later, but as you're going, it's really important that you read the volumes off the side of the syringe and record these next to the masses in the book. So when I've got 1.5 kilograms on there, my syringe is measuring 49 milliliters, so I would write that down. So once you've recorded the volume and it's returned to thermal equilibrium, you can add the next mass on. You'll get a little blip in the temperature again. Just wait until it returns to the room temperature, because remember we're making the assumption that this is isothermal at this point. And then once it's returned to the room temperature, read off the volume. In my case that's 46 milliliters, and record that in your book. You keep on doing this until all the masses have been added to your system, giving it time to return to thermal equilibrium and recording the volume every time. Now that you've recorded your data, it's time to analyze it. So you should have graphs on the screen which look a lot like this. Now what we need to do is get the mean value of the pressure in each of these regions and measure the temperature once it's returned to thermal equilibrium as well. So to do that, hit this little highlighter button, and then we need to adjust the size of the box, and then we'll drag it to the area that we're interested in. So this here shows me the initial pressure. This was before I added any masses. So to get the value for that, I then, once I've put my box over it, I hit the little sigma button, which gives me the statistics. So this will tell me the mean. I can choose other statistics if I want, but what I'm interested in is the mean. So what I can do is I could move this box around to each of these places, or I can create a new box, whichever one you prefer for each region. So now we've got the box, we put it on here, and this is when I'd added 1.5 kilograms. So let's just get it to thermal equilibrium and then hit the statistics button for that box, and it tells me that the mean is 124.8. So I would then record that in my box next to the, in my book, sorry, next to the 1.5 kilograms. Now I just do need to check that it's returned to thermal equilibrium each time. I expect these temperatures to be the same, so I create the boxes over here as well. Here's the temperature before I added any masses, so get the statistics on that, and then you can see the blip when I added the masses. What I'm interested in is the bit after it's returned to thermal equilibrium. So let's drag this box and put it there and just make it a bit thinner. Get the statistics for that box, 30.35, so you can see it is returning to pretty much the same temperature like it was meant to. So fill out that table in your book, and then you can answer the questions about what happened. In part 2 of this experiment, you're going to be taking the air inside the cylinder through a cycle. So to do this, you're going to need to push down quickly. So remove the syringe from the clamp. Now for this part, you're going to need 40 milliliters of air in the syringe. So remember, to change the volume of the air, you need to disconnect the pressure sensor, compress the syringe down to 40 milliliters, and then put the pressure sensor back in. So now it's all connected up at 40 milliliters. What you're going to do is an adiabatic compression, so a quick compression. You're then going to hold it down there while it comes to thermal equilibrium with the surrounds, and then you're going to very slowly let it come back up, and while you're doing that, you're going to try and keep the temperature constant. So before you start the process, remember to collect the data, press start, then quick compression, hold it there while it comes to thermal equilibrium, which you will see on your temperature graph. It will level off and go horizontal. Once it's horizontal, let it go up very slowly, trying to keep the temperature line as horizontal as possible. And it should end up returning to the 40 milliliters that it started at.